Yeah, my name is Omar Yaghi. I'm at the Department of Chemistry at the University of California, Berkeley, and I'm delighted to be here to share with you some of our results on harvesting water from desert air. Before I start, I want to thank the organizers for putting together this wonderful conference on this important issue of water. This is a map of the world indicating the arid regions of the world where water is scarce. So almost 1/3 of the world population lives in water-stressed regions. And even in those regions where there is plenty of water, let's say the watered regions of the world, there are many questions about its purity. And then, of course, there's the other factor that 160 countries import their water, and this is a national security issue for many countries. So, fortunately, there is a solution that might give independence to water, especially drinking water, and that's the fact that there are many liters of water in the air at any one time. 3 sextillion liters of water in the air at any one time. This is a resource that we could use. It's recyclable, and if we can harvest this water, we can deliver clean drinking water to the world and provide citizens of the world with independence in terms of access to water. So the idea of harvesting water from air is not new. There are products out there, as you can see here, where this could be done. However, the limitation is that they all work very well when the humidity is high, above 60% relative humidity. And anything below 60%, there's such a tremendous energy cost that it's really that they do not work. So these, you can think of these as working only at high humidity. And there's absolutely nothing out there that works at lower humidity, especially humidities where these red regions are usually most of the year experience. So it's these regions where we need materials that could harvest water from air in an energy efficient way. And if we can invent materials that harvest water from air in these red and orange regions, then we could also harvest water from higher humidity. So a material that works in arid regions will also work, of course, at higher humidity. So my vision is that could we harvest water from air anywhere in the world at any time of the year? Let me just explain why is it so hard to capture water from dry air. Let's say that I'm in a city right here, A. I'm at a city where the temperature is 30 degrees and the humidity is 20%. Okay, in order for me to take that water out of the atmosphere, I need to cool down the air to 4 degrees C. Okay, that's a lot of energy that I need to put into the system in order to cool down large amounts of air so that water can be condensed. Now, if I have a material like a porous material, as I will show you, you could harvest that. This material would have to be capable of harvesting water from low humidity. And in so doing, you're actually increasing the humidity in that material. And if that material, of course, is in a system, you would have created higher humidity. And therefore, condensing that water will not require more than a few degrees of cooling. So you cut down the energy penalty if your material could produce this higher humidity. And so, as I said, there are no materials that can do this. And the materials that are being investigated today are shown here: zeolites, polymers, hydrogels, and molecules and salts. And in order for any material to be able to do this and achieve commercialization, they need to have high capacity so that you are not running too many cycles. You need fast kinetics so that water is going in with ease, you take it out with ease without having to heat or apply heat. And you need the material to work at low humidity. As I said, materials that work at low humidity will also work at high humidity, and therefore perhaps we can achieve our vision of harvesting water anywhere at any time of the year. So you can see that these materials, although very attractive, fail in one or more than one of these categories, making them not so viable in this application. We've, for the last 25 years, we've been developing an area we call now reticular chemistry. And in this area, we have produced new materials we call metal organic frameworks, which we showed that they can be crystallized in 95. And then we showed their porosity in 98. And then we showed their ultra high porosity in 99. We also showed in 2005 and 2007 for the first time that porous materials made entirely of covalently organic linkers, again crystalline, could be made. And through the pipeline, we also have molecularly woven structures. But I will discuss today only the metal organic frameworks. These are made from metal oxide units that act as nodes and organic units that act as struts. The nice thing about reticular chemistry is that it covers three important components, and that is molecular building blocks. So you put the material together, stitch them together through strong bonds to make robust materials. And it's crystalline so that we know exactly where all the atoms are, and we know how to modify the material with great definitiveness. So these materials are well suited for many applications. Just to give you an idea where the chemistry is today, there are many inorganic units that could be used, many organic units that could be used. And 1,000 inorganic units is an underestimate. And 1,000 organic units is an underestimate. But just for the sake of this thought exercise, we say we have 1,000 inorganic units that are combined by 1,000 organic units. And then, of course, the organic units can also be functionalized and modified. Let's say that we can put in 1,000 side chains as indicated here. And we've already identified about 100 different applications, including water harvesting from air. And you have many, many frameworks into which these building units can fall into. And so very quickly, you realize that you have infinite chemistry. We have been able to discover an infinite world of chemistry, materials, and applications. So these materials are now being practiced all over the world. This is when we first started back in 1995. This is my group in the US with 2 publications. And then as you can see over the years in 2000, many other countries, investigators from many other countries came in, and this is 2010. And now in 2020, when this study was done, almost 102 countries around the world have institutes and researchers working on MOFs. So this, what I'm trying to say is that MOFs are available to the world for any of these applications, including water harvesting. So we've been investigating different gases, including carbon capture and methane and hydrogen, but today I'm going to focus on water. So we discovered back in, and published this article back in 2014, that this MOF, it's a zirconium MOF, made from a metal organic, excuse me, takes up water at room temperature or at 25 degrees in the red line. And the amazing thing is that we saw that it takes up water at low humidity. This is a humidity of around 20% relative humidity. That was unique. And what was even more unique than that is the fact that you can remove the water by just heating to 45 degrees C. Now, there are desiccants known to take up water at room temperature, but then you have to heat them up to over 200 degrees C to get the water out. But in this case, because of the metal organic composition, we can modulate the hydrophilicity of the pores and be able to remove the water at fairly mild temperatures. So this, for people like me who grew up in the desert, this is ideal for harvesting water from desert air, because during the day I can take up the water, during the night I can take up the water, and during the day when it heats up, I can remove the water. And the fact that I have this very sharp knee isotherm means that my working capacity is maximized. So the shape of the isotherm indicated to us that there is, unlike any other material, that there's a cooperative phenomena going on in terms of binding water into the pores. So we try to recycle water to make sure that the material is stable. And you can see here 80 different cycles with absolutely no imprint left on the MOF in terms of its performance. Except we saw that after the first cycle, the material lost just a tiny bit of its performance, just a few percent of its performance. Then we have a constant performance. This meant that some of the water that goes in first is actually staying in the pore. So it turns out that from X-ray diffraction studies on single crystals, we find that the first water molecules to enter the pore interact with the metal oxide units, and they form, one can say, a layer onto which other water molecules bind. And it was these water molecules that form in this configuration and then in these configurations that act as seeds onto which water molecules can bind and fill the pores. And these initial water molecules are not taken out during the water harvesting process. So they just sit there and they are used as seed to grow the water structure into the pores. And it is then these other water molecules that come in that in the end are taken out, and then new water comes in, and then the process is repeated. So we wanted to show that in fact this works outside the laboratory. And so we have put together, in collaboration with Evelyn Wang, a device that is almost the size of a hand. And this device employed 2 grams of MOF, just 2 grams, just to demonstrate that it can work outside at a relative humidity of around 25%. You see here that as the box is exposed to sunlight, the inside of the box heats up 50 degrees C, 60 degrees C, and so on. But as it heats up, the water comes out of the MOF. You can see here droplets that grow larger and larger. Okay. And this was very exciting because it means that the MOF can work in real life conditions. Obviously, we can't water the world with just these few drops. So what we wanted to do is show that this can be scaled up, at least in a laboratory device, a laboratory-based prototype. So we used a different configuration of this prototype, and we employed 1 kilogram of MOF inside this box. And we place this box inside a larger box. And the idea is that the larger box is open during the night, desert air comes in, MOF traps the water. During the day, you close the outside box, and when it's closed, the sunlight heats up the interior, water comes up and condenses on the walls, then you can collect drinking water. So this worked in the lab, and then we took it to, this is what the box looks like, just before I show you the results. This is what the box looks like. It's made entirely from simple materials like plexiglass, very inexpensive materials, and very cheap. And this is the result. The result is that in 1 kilogram of MOF, we can harvest around 200 or 300 milliliters of water, so a bottle of water for each cycle. The MOF can stay in the device for the lifetime of the device, for years. Okay, it can be cycles, very stable, you don't have to replace the MOF, and it works with absolutely no power input aside from the energy that's coming from sunlight. So this is the water that was harvested, is pure, and it's been tested for the presence of any impurities, metals, organic, they do not exist. This is pure distilled water, which is the student took it upon himself to
ready,
drink it.
3, action. Cheers. Nice.
Okay, very good. So we wanted to go on. That moth was a zirconium moth, and zirconium is rather expensive. So we wanted to move and make, based on our knowledge of how the moths behave, we can now use reticular chemistry to make an aluminum moth. Aluminum is really dirt cheap. And we combined it with this organic linker to make a new porous structure. We call it moth 303. That works even better than the moth I just showed you. So let's take it to, so for this particular one, we designed what we call an active prototype, and it's based on moth cartridges that are placed in the device in such a way as when some cartridges are collecting water, the other ones are releasing the water. So this one is active, meaning that we wanted to do more than one cycle a day. And so we use a solar panel to provide power for a fan that pushes air into the moth and allows you to also heat the moth so that you can control the uptake and release of water. Again, for a 1 kilogram device, we went to the Mojave Desert and showed that in fact it works in one of the driest deserts in North America. And that is, you can see here, if you monitor the relative humidity right here, I would like you to focus on this panel. You see that during the night, the humidity is high. During the day, the humidity is extremely low. It goes down to almost 10% relative humidity. And whether it's during the day or during the night, you can see that we are harvesting water. Okay, and that's the power of this moth, is that the moth works at temperature as at ambient temperatures, but it also works at very low humidities, and it can operate for 24 hours. You can see here the water is being harvested from air and drips are coming directly. This is real time picture or video of the water being harvested into the moth and released. Now, these are the students who went to the desert, and you can see one of them holding a liter bottle of water that was just harvested the night before. So the reason these results are very, very exciting is because this moth not only takes up water at low humidity, but it releases the water within minutes. And you can heat it up to 50 degrees or all the way up to 85 degrees to control the kinetics. But even at these mild temperatures, you can see that in less than 3 minutes, we can release all the water. And that meant that under the right conditions, one can design a prototype that can cycle water for many, many cycles, hundreds of cycles a day. And so this is our latest generation of water harvesters. And this device employs only 100 grams of water. Let me repeat that, 100 grams of water, 1/10 of a kilogram of water. And with 100 grams of water that stays in this device for many, many years, every day, you can harvest 4 liters of water, okay? So 4 liters of water a day based on 100 grams of moth. And that's because the moth extracts water readily, and you can remove the water from the pores without having to heat to very high temperature. And so you can do many, many cycles. This is a video of the device, which I'm gonna try to play, but I'm not sure if it would work as well. This is where the water droplets are forming, and water will be collecting here. This is a bottle for ultimately water collected. This is, you can see the water collected here. And now the water is being filled into the bottle. Okay. So this device has been working for 2 years in the California atmosphere and weather, including when we had fires. There is no reason to filter the air because the MOF itself is a molecular filter and only takes up water. In case of gases such as carbon dioxide that may go into the pores, they can be easily removed because water sticks tighter to the pores than carbon dioxide. So the water you get is absolutely pure and has no impurities, and it meets the FDA standards in the US. So based on these results, it's very clear that using reticular chemistry, we can improve in a very short period of time, the harvesting of water using MOFs. And once we have figured out a way of using the entire MOF particles that are in the material, we would be able to harvest for each kilogram of MOF 100 liters a day. Okay, and as I said before, the MOF does not have to be replaced. It can stay in the device for many, many years and delivering on a daily basis. If you have 1 kilogram of MOF, you're delivering, the expected delivery is 100 liters per day. So based on these results, we have modeled these MOFs for different parts of the world. And you can see here the driest deserts in the world. And even at the harshest conditions, you see that the MOF is delivering 4 or 5 liters a day. Okay, and the rest of the year, you're harvesting almost 40 liters a day. So depending on where you are in the world, whether it is the Atacama Desert in Chile or Mojave Desert in California or Lanzhou in central China, Kabul, Riyadh, Baghdad, New York, Stockholm, Los Angeles, London, Granada, Rome, Perth, Cape Town, Delhi, and Dhaka, all of those, humid or arid, could be harvested. The water in the atmosphere could be harvested by these MOFs, and you get the delivery that is shown here on the left. So I think that we are, I would say, beginning to achieve the vision of water harvesting from anywhere in the world at any time of the year. And accordingly, we have a startup that is already producing these countertops 4 liters per day. Our vision is to go for household devices that produce 200 liters per day. And of course, village scale devices that would produce 20,000 liters per day. So the point is that using the MOF, you're delivering pure water, and this water could be used for drinking, could be used for agriculture, could be used for many different applications. So if you're worried about us taking the water out of the air, well, first of all, the water goes back into the air. But also, look at this. If we serve 50 liters to every citizen of the world, we've only used 0.002% of the water in the atmosphere. So there's plenty of water in the atmosphere, and this is a way to harvest it in a recyclable way. I think the impact is that we're delivering pure water in a distributed mobile off-grid, which can be personalized. And especially interesting to me is that we can achieve water independence regardless of where we are and where we live. So thank you very much. This is the conclusion slide, is that this is a result of reticular chemistry, which is a control of the strong bond. And I want to acknowledge our collaborators, especially at CACST, where we have a joint center between CACST and UC Berkeley, the Joint Center of Excellence for Nanomaterials for Clean Energy Applications. And I especially want to mention Prince Dr. Turki Al Saud, who has inspired this project and was an early supporter of the project, as well as our current director, Dr. Majid Al Awad. I want to thank them and thank CACST for their generosity with their time and their expertise and their efforts together with us to address one of the most important problems facing the world, and that is the water stress problem. I want to acknowledge my students, in addition to those acknowledged in the presentation, for all their contributions and work. And I want to thank you for your attention.